Hello, this is Lab 4, Oscillations. The purpose of this lab was to analyze the motion of a mass on a spring in both the x and y directions and observe the energy principle in real life. The model of the mass on the spring was made using glow script. The prevalent physical principles evident in this lab are the energy principle, specifically potential energy, spring and gravity, kinetic energy, Newton's second law, the spring force, and gravity. The main results of this lab were that the model and experimental exposition versus time graphs line up nicely, and the estimated period was about 1.52 seconds when we used the motion in the x direction to estimate it. Additionally, the model and experimental y position versus time graphs have the same general shape at around the same time, but the mass does not move as much in real life. The calculated period using the y positions was about 1.61 seconds. One of the main physical principles evident in this lab is the energy principle, which states that the total change in energy in a system is equal to the work done on the system. The total change in energy is composed of all the changes in the different types of energies in the system, which in our case is kinetic energy, calculated by having the mass times the squared speed, the spring potential energy, calculated by having the spring constant times the square displacement from the equilibrium position, and the gravitational potential energy, which is calculated by multiplying the mass, change in height, and acceleration due to gravity. We also needed to calculate the force of gravity and the spring force in order to calculate the net force acting in the system, and then update the position and velocity of the mass using the momentum principle, also known as Newton's second law. All relevant equations are shown here. In the experiment, I used a video of a mass on a spring being released and analyzed its oscillating motion in both the x and y directions. I then copied and pasted this data into an Excel file and converted it to a CSV file in order to compare it to the model. The system was the mass, the spring, and the Earth. The surroundings are the rest of the universe. The mass had an initial position of negative 0.11 meters in the x direction and negative 0.63 meters in the y direction. It had an initial velocity of 0.088 meters per second in the x direction and negative 0.13 meters per second in the y direction. It has a mass of 0.402 kilograms. The net force was calculated by calculating the gravitational and spring force and adding them together. The total change in energy and change in kinetic and potential energies was calculated using their respective equations. The velocity and position of the mass were updated using the momentum principle. This is the change in energy versus time graph. This is the x position versus time graph. And lastly, this is the y position versus time graph. The similarity between the experiment and the model is that the x position versus time graphs line up nicely, apart from a small discrepancy. The differences include that the experimental y position graph has a lower amplitude than the model, and the experimental y position versus time graph is also shifted more to the right. Additionally, the model and the experiment start at slightly different times, but I could not figure out a way to fix this. The energy principle seems to be satisfied. The work done on the system is zero because everything of interest is in the system. This means all the energy changes should add up to zero. The total energy change in the graph seems to stay at zero. Additionally, at every x value in the graph, subtracting the sum of the spring potential energy and the kinetic energy from the gravitational potential energy seems to also give a value of zero. However, it is hard to be precise because the tracking method does not collect continuous data, so we had to extrapolate in order to create a graph. The estimated period using the x position was about 1.52 seconds, and the estimated period using the y position was about 1.616 seconds. Both periods should be the same, as the period is defined by 2 pi times the square root of the spring constant divided by the mass. Essentially, the period of oscillation is a property of the spring and the mass, and not from the initial conditions in either direction. The discrepancy probably stems from errors in tracking the motion of the object and the inability to precisely calculate the period. Thank you for watching and have a great day.